right, so probably the most confusing thing of everything to do with helicopters is the flight controls. With our ailerons on regular airplanes, you simply pull back, you get a little bit of deflection, the plane goes up, or push on the rudder, airplane goes side to side. The helicopter, though, is a little bit more complicated than that. There's a lot going on with the helicopter that allows them to hover and then have this 360-degree freedom of movement. And so understanding the flight controls can be a little bit of a challenge. So let's take this slow and let's try to really get it into our heads. All right, there's four fundamental flight controls in a helicopter. Each one, if you manipulate it, you're going to affect all three of the other ones. So it makes helicopter flying quite challenging, but once you kind of get it figured out, it's not that bad and it's very rewarding. I mean, there's not many devices that can just hover right at the treetop, fly at 200 miles an hour or almost 200 miles an hour, and land anywhere you want to go. So definitely well worth the investment of time and money into figuring it out if it's available. So let's just start. We'll name these four, and we'll kind of go over what they do, and then we'll look at them each one of them a little bit more deeply. First, you have the cyclic. That's going to or is going to decide which way the helicopter goes. The collective will affect the pitch in the blades, and they'll allow you to go up or down, faster or slower. The throttle is what affects the engine, how much gas is going into the engine, which will allow the engine RPMs to increase or decrease and feed the transmission and then therefore the rotor hub the effective amount that's needed. And then the pedals affect the pitch of the blades in the tail rotor, which then allows for the tail rotor either to have greater torque than is being placed on the helicopter body by the main rotor, or less torque by the helicopter body by the main rotor. Like I stated before, the collective, essentially you pull up on it, and as it pulls up, it moves several links that then changes the pitch of the blades. This allows the helicopter to climb. It allows it to get a bigger bite of the air, so that way you can translate that into forward motion whenever it's tipped forward. And it really is kind of the under-celebrated or underappreciated flight control of a helicopter. The cyclic is cool and all, but it's kind of intuitive. You would expect there to be a device that you could point it in a certain direction or move it around to cause the helicopter to go a certain way, and everyone would expect a throttle. And pedals seem to be ubiquitous with aircraft or somewhere, even though a helicopter's works different than say like an airplane's pedals, but they accomplish the same thing. The collective is really fundamentally unique to helicopters, and it's something that you'll have to work on and rig. The cyclic generally stands in front of the pilot and the co-pilot's legs. It just sits right there, and you grab with one hand on the cyclic, the other hand on the collective, and you manipulate the collective in the way that you want the helicopter to go. So if you want the helicopter to go forward, you push forward, and the helicopter will translate forward. If you want to go back, you pull back on the cyclic, and it drifts backwards. So it does this through a series of push control rods. And changes the pitch change lengths all up to the swash plate, which we'll get to here in just a second. And that then changes the pitch of the rotor disc as a whole, whereas the collective affects the individual blades. The cyclic affects the rotor disc as a whole unit. So the rotor disc needs to pitch forward, or the rotor disc needs to pitch back. Now keep in mind, as you move the cyclic around on the ground, you'll see those pitch change lengths move up and down. That if you were to go forward, you're actually going to see the right side of the pitch change lengths push up because of gyroscopic precession. That as you input the controls, you're only get the effect of the spinning disc 90 degrees in the direction of rotation. So you'll see the rotor disc come up. Same thing if you were to pull back, you'll see it on the left-hand side come up. And so it can be kind of confusing until you understand what's going on with gyroscopic precession and the cyclic. All right, the pedals that are in the helicopter will effectively control the yaw direction of the nose of the helicopter. You step on one pedal, it yaws to the way that you stepped. You step on the other pedal, it yaws the way that you stepped on that side. And this is pretty well ubiquitous across all helicopters. This is just how they work. Now, it accomplishes this directional control by changing the pitch of the blade. So you can really think about the rotor pedals as like a collective, but just for the tail rotor. When you press on the tail rotor in one way, it's going to pull on the blades to get more pitch, so that way it increases the anti-torque force being pushed on the body of the aircraft to overcome the torque force of the main rotor. If you push on other pedal, it may flatten it back out and take some bite out of the tail rotor, so that way the torque force of the main rotor can overcome the tail rotor and spin the helicopter around. And that's how directional control, or at least your yaw control, happens in a helicopter. Probably the most under-celebrated flight control of a helicopter is actually the throttle itself, because in an aircraft, there's only, or in an airplane rather, you add power and it'll cause the plane to climb. You can take power away, it'll cause the plane to descend, but it's still not the fundamental way that you cause the airplane to pitch one way or the other. On a helicopter, it's even more complicated, because as you increase, like let's say you want to climb a helicopter and you pull collective and you increase pitch, that extra load on the rotor disc slows the rotor disc going around. It's real simple. Like if I told you to run 100 meters, you would run it. Now if I gave you a baby hippopotamus and told you to run with it 100 meters, you would run a lot slower because there's a lot more weight like in your arms. This is no different. Like if you pull pitch, the rotor has to move that much more air because of the increased angle of attack on the rotor disc, and it slows the rotor from spinning around. Well, whenever that happens, you have to compensate some way, shape, form, or fashion, because if it doesn't spin at a certain rate, the helicopter can't maintain straight and level flight, or I guess in this case climbing flight. It can't stay in the air. So you have to roll the throttle on to increase the amount of RPMs coming from the engine into the rotor disc to compensate for that, and to kind of keep it right there in that sweet spot, in that little green range of your NP. Now, the same thing happens if you deload the rotor disc and you drop the collective and the helicopter wants to sink. You don't want the engine RPM to spike, because all of a sudden now there's no load on it. It can just keep on going. Like it'd be like if you had a diesel that's trying to pull something like way uphill, and all of a sudden you detach the trailer, it's going to just take the same amount of power, but like a fraction of the weight, and just launch itself over that hill. You don't want that. And so whenever you drop the collective, you have to roll the throttle back down to keep that from happening. Now this all gets overcome by using FADEC, or full digital engine control, to keep that from happening. All those helicopter controls put together creates kind of like a dance. You'll see helicopter pilots sit there with a cyclic and they'll go forward, but because they've gone forward, they have to pull a little bit of collective as well. And then as they pull a collective, they have to roll the throttle on, which then in turn causes the helicopter want to yaw, so they put a little pedal in it as well, which then causes other flight control feedback. And they constantly are just doing this movement, even if it's just like small, slight movements. It's this perpetual dance that the helicopter pilot has to do. Now, automation helps that some. The FADEC definitely helps the throttle portion of it, a lot. And you can get other INS-based avionics that help keep the helicopter where it needs to be. In terms of us as mechanics, we spend a lot of time looking at like stability control augmentation systems that help the helicopter stay straight and level, or auto hover systems. We also have to think through rigging a helicopter, and rigging a helicopter can be quite a challenge because everything has to be precise. When we would do an OH-58, it could be a 2 or 3 day long process before we finally get it right. It's easy to get to like 90%, but then that last 10%, you're constantly making small movements. But we'll get to flight control rigging next. All right, so how do we rig a rotor system? What goes into that? And this is something that if you're a helicopter mechanic, especially if you're on the line, you'll end up spending a lot of time doing this, because helicopters naturally, they just want to fly apart. It's kind of an old adage that an airplane wants to fly and a helicopter wants to brake. And so you'll spend a lot of your time doing your track and balance and rigging the flight controls to make sure that they stay exactly the way that they're supposed to, and that they don't get out of track or out of balance, or so on and so forth. So let's talk about that. All right, when rigging a helicopter, it's not really that hard. It's not totally difficult to do. It's just simply following the directions. But you absolutely have to be right on the money with the procedures from the manufacturer, because there's a high degree of precision that needs to be made in order to do it correctly. Now, if you don't rig the helicopter correctly, there's any number of like catastrophic things that can happen, and maybe even not right off the bat, just like whenever they get in certain flight profiles. So you definitely want to be very cognizant of the maintenance manual and do it exactly the right way. Additionally, if you follow the book verbatim all the way through, you're going to get through it a lot faster. If you start kind of like winging stuff or getting sloppy, you're going to end up tied down into this rigging job for days on end. All adjustments, clearances, and tolerances have to be exact. There can't be a whole lot of tolerance, one way or the other. It has to be exactly what they tell you to do. Now, rigging of various flight control systems can be broken down into 3 main steps. First off, you have to place the flight control system in a specific position, holding it in position with pins, clamps, jigs, or adjusting various linkages to fit the immobilized control component, meaning that in order to rig everything right, you have to start from a known point, and that known point is usually provided for you in the way of a jig, or there might be lockout pins or control pins that keep the cyclic or collective in a very precise place, and then that lets you know that since the cyclic is at this one position, you can now rig the rest of the flight controls to make sure that you get out of the helicopter what the pilot is wanting from that one position. All right, then after you've done that, placing the control surfaces in a specific position using a rigging jig or precision bubble protractor or a spirit level to check the angular difference between the control surface and some fixed surface of the aircraft is the next step. So you'll go up to, once you have the flight controls locked out, you'll go up to the actual rotor itself and say like, hey, where does this control surface need to be in order to get to the angle in which the actual flight controls your cyclic is set at. Like I said earlier, we used to do this all the time with the tail rotor on the OH-58 because we would end up taking fire on the tail boom. The tail boom would have to come off, and then part of the putting the tail boom back on is re-rigging the tail rotor drive shaft, which was where the bulk of that work seemed to lie. However, you would also do it in the main flight controls as well at different points. Now, what we'd end up doing is that we would go back with a propeller protractor on the tail rotor prop and actually set it up and set it to a certain angular set, preset. So say it's supposed to be set at like 30 degrees. So we would adjust the PC links on the tail rotor until it got to that 30 degree, and then we would rig all the way to up to that point and make sure that everything that we had set in line would put the tail rotor at 30 degrees whenever the pedals were at a flush position. You would do the same thing with the cyclic. You would put the cyclic in one place and then rig it and make sure that the blades were set in a certain position, and then you would rig all the way up so that way it's nice and even. It's set exactly the way that you want it to be. Now, once you have all of both the flight controls in a known point and the blades in a known point, the next step is to simply go through and start making adjustments so that way those two known points line up. And so that way you don't have the cyclic at a neutral position and the blades are in like full tilt or something like that. You just make those adjustments, and then once you have that both of them in a static position, we'll call it, you're going to make certain movements. You're going to move the cyclic to a certain place and make sure that the blades follow, and then make adjustments as needed, and then go back to neutral. And whenever you go back to neutral, they should return to neutral. After that, it's a simple test flight, and then as you test fly, you're going to check different friction levels and pull strength. So you take a spring scale, put it on the collective, and pull up, and it should move at a certain level of certain poundage. But that's how you rig a helicopter's flight controls. Okay, so the big task that comes with all rotorcraft is the track and balance. So it's the trying to keep it like from hopping like this up and down, and make sure that the rotor blades actually stay in a level plane. That you don't have one that's up here, one that's down there, and you lose efficiency that way, and you pick up a big vibration. So let's talk about track and balance. The different ways that we can track and balance helicopters, from the old chalk line, light gun, all the way up to other accelerometer based systems. All right, so one of the first and simplest ways that ever came about of trying to figure out how to correct blade tracking is the flag and pole method. So essentially, this is pretty simple. The blade tips are marked with chalk or a grease pencil, and each blade tip should be marked with a different color. So that's another thing is that all the blades are typically like the red blade, the blue blade, the green blade, or whatever, depending on what how many blades that you have. So anyways, as they come around, then the chalk method, or you take the little flagpole and stick it to the rotor blades. The chalk method will slap the white curtain that's there and make a mark, and then you'll know that the red blade's high, the blue blade's high, whatever, one's low. And then you go back to your PC links, which is a lot like just a turnbuckle, and you make so many, we would count flats in the Army, like so many flats. So you would break torque on the PC link, run the jam net up, and then you would turn the PC link so many flats, and then run it back down, retorque it, re-safety everything, and then run the helicopter again. And as you ran the helicopter again, you would make it, if you're using the we never use the flag and pole method, but if you were using the flag and pole method, it would make another mark, and you would know if you made the right corrections or not. And presumably the maintenance manual would have, if this is the preferred method that's you're being told to use in the maintenance manual, it would say like, hey, look, if the blade is 2 inches high, adjust the PC link by so many inches, and because they know how long the blades are going to be, and they know how many inches or what fractions of an inch the PC link will extend or contract, and so therefore you would know mathematically, like if it's the blade is 3 inches high, we need to have so many flats on the PC link to bring it back down. But that is the flag and pole method. Now, the probably the most common way to actually get this done is to attach. If you'll notice at the end of every blade, like if you remember when we looked at blades in the last video, there was like a little tie down to tie the blades down so they didn't spin around. Well, the real purpose of that thing is to attach little flags, and these flags correspond with the color of the blade. So if it's the red blade, it gets a red reflective flag that hangs down, so that way the pilot can see the flags. Then as you run the aircraft up, you get to a certain rotor RPM, so you know the speed that it's going. And you take this light gun, you aim it at the rotor blades, and you pull a trigger. Now it has a strobe light at the end of it that's flashing, and then the blade, you will be able to see where the blades are actually going. You'll see, if the red blade is low, you'll see a low red flash as the strobe light reflects on the red rotor blades. And then if the blue blade is high, you'll see blue. And the idea is to slowly bring those two colors together. And so you make whatever adjustments that you need to make to get them to where you don't see independent colors, rather than you just see like this kind of like blur that's right in front of you. Now, this is it's an older way to do it. But it's also the simplest and probably the cheapest way to do it, so it's probably the most common. All right, this is a balance kit for a Black Hawk helicopter. A couple of things that you'll see in it. There'll be a bunch of weights. You're going to have a scale. You see it on the bottom right-hand corner, and the tools that you need to take the. And I've never done a Black Hawk balance, so you have to forgive me on the particulars of it. But essentially, in order to install the weights as needed. Now, like, why would you need to put on or take off weight from a rotor hub? Well, if you think about it, think about the like a wash machine. If you take all of the clothes on your wash machine, you put it all on one side and you leave the other side blank, and you turn the wash machine on, it's going to make a horrendous noise and be shaking all over the place because it's out of balance. However, if you disseminate the clothes to where they're equal all the way around the wash machine, you turn it on, it'll work just fine. This is no different. It's the same thing. It's just that you have more weight, more and at a higher RPM, and it costs a lot more than your wash machine. So what you want to do is make sure that the rotor blades are balanced out. Now, every rotor blade has a certain weight to it, and it'll be usually in grams typically, and so let's say you have one rotor blade that's on a two blade head, that's 500 grams, and you have another one that's 450 grams, and you install it, you don't install any extra weight, and you turn it on. That is going to shake that helicopter to death. Well, so what you have to do is you have to go back and you have to put 50 grams on that 450 gram blade to level it out and make it work appropriately. Now there are little nuances. So let's say that 500 gram blade, because it's an older blade, it's eroded on the tip, particularly a lot, and like there's maybe some other little things that have happened to it. Maybe it got dinged or chipped or something somewhere on the blade. And so even though the tag says it's 500 grams, it's actually only like 490 grams. But more importantly, the 10 grams that's missing is on the very, very tip. So if you remember from our basic physics class, because the 10 grams is on the very tip of this very long arm of this 20-foot rotor blade, that 10 grams has an outsized effect on the helicopter itself because of that extra arm. So you have to take those things into consideration. So whenever you go to do balance, even if you have like a tool, a computer that's telling you, oh, you need to add so many grams to this blade, the computer can't see where the blade is. It can tell, hey, look, this blade is clearly not weighing 500 grams because it's behaving in a way that it shouldn't. So therefore, you're going to have to add some weight to it, or maybe take some weight off of it, and so. But it doesn't. What the computer doesn't see is like where that weight, went missing. So you have to play with the machine a little bit. Like I was saying earlier, that test pilot friend of mine, he would always, take and reduce whatever the machine told him by about 75%, and that would kind of give him a starting point. Now, usually the machine was pretty close to right, but he would start from being low and then try to make things better rather than install a bunch of weight and then all of a sudden it gets like way worse and they have to start take it away from the other direction. But that's it. So every helicopter is going to have a balance procedure and parts that go with it, but the general gist of it all the same. Once you have the rotors in track, then you can start to worry, iron out the vibrations by making sure that it's balanced. Now, different drive system vibrations that you'll encounter will generally mean different things. You can tell, like you'll have vibrations that seem to go backwards and forward, up and down, side to side. Now, you've heard me talk about having like a 1-to-1 hop, or a hop of some variety. Now, the to break that down, a hop is simply just a vibration. So it's just helicopters just bouncing up and down. The 1-to-1 ratio that comes to it is the ratio between the frequency of the vibration, so how fast it's going, and how many revolutions the helicopter blade is making. So a 1-to-1 hop is it's happening every second per every time it takes the rotor blade to circulate. So it's happening a lot. It's like high frequency, just like boom, 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 jumping up and down. All right. So the way the way the FAA breaks down different levels of helicopter vibrations is in its frequency, so from extreme low to high. So we're just going to go through these. So extreme low frequency is usually indicated as a pylon rock. It means that the pylon is you can feel like it's kind of going like bump, 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 bump. It's like really slow, and it's just the whole pylon is going one way or the other. The other one is low frequency, so 1 revolution or 2 revolution type vibration. So it's going to be a little bit more aggressive than what you would want to be, and that's usually just like a blade that's developing more lift than the other one, so it's probably pitched up. You probably need to adjust the track or check the rigging of that blade in itself, or the blade has become damaged or eroded to the point that it's starting to cause these kinds of problems. The medium frequency vibration is an increased level of the same vibration, but it's caused by a change in the capability of the fuselage to absorb vibration, or maybe a loose aircraft component like the skids or whatever. So it means that the airframe is not absorbing the lower frequency vibration, and so now it's making it feel a lot worse. And so you kind of start going around and start jiggling some things, see if you can figure out what the problem is. High frequency vibrations, however, are going to be an indication of something to do with the tail rotor, and that's because the tail rotor is a fraction of the size of the main rotor. So anytime you feel like any shimmying, especially in the rotor pedals, if you can feel it, especially in your butt as you're sitting in the helicopter, and it's a really high frequency, like just feel like somebody's shaking you really really bad, it's likely going to be the tail rotor blade somewhere in there, and so that kind of helps your troubleshooting from there and working your way back. Now all of these are kind of general rules of thumb. A lot of this is the diagnostic portion of it is going to come from just simply time working on helicopters, and you'll start to see, especially if it's the same type of helicopters over and over again, you'll realize that the helicopters have certain characteristics about themselves, and every different model and type has different characteristics. And so the more that you spend with that one type of helicopter, the better you're going to be getting at diagnosing, these types of things. I knew a test pilot whenever I was about 18 years old. I was walking out to a helicopter with him. He looked up at the helicopter and he goes, "Hey, the red blade is high on that aircraft, and you're probably going to need another like 40 grams on the opposing blade." Now he could do that just by looking at it, by sitting in the helicopter, because he'd been doing it since Vietnam. He'd been in the army like for 40 years or something like that at that point, and so he had just a lot of reps in troubleshooting these types of problems, and that's really what a good helicopter mechanic is going to be like. It's just somebody with a lot of experience on them. Now you can take the maintenance manual and you can get there. It's just you're not going to get there as fast as somebody who's just done it a lot, which kind of goes without saying. So don't just know these are just kind of like kind of point you in the right direction, and they're not the end all be all at all.